Okay, hello everyone. So in this lecture, I'm going to give you a brief introduction to computational fluid dynamics and different methods and approaches that we have to resolve turbulence in a fluid flow. So I am going to give a brief introduction of three major methods that we typically use in turbulence predictions and talk about their differences, the advantages and disadvantages of each of these methods. And some of these methods are actually based on the theories that we learned so far in the course. So let's get started. So the first and simplest actually model and kind of approach is called direct numerical simulation. So in direct numerical simulation, what we do is actually we resolve all the turbulent eddies in a flow. So imagine we want to solve, say, the flow of the wind or the atmospheric boundary layer around these kind of buildings in a city. As you see, the flow is highly turbulent and we have fluid structure interactions, especially near the buildings. We are going to have very high Reynolds number and highly turbulent flows, and you see different scales of flow, different turbulence, as you see are observed here in clouds, and also they are apparent in winds as well. In the wind structures, you see these different coherent turbulence structures and different turbulence patterns. So we have a large range of eddies here, as you see. So this is kind of an asymptotic way of showing those. So in the direct numerical simulation approach, we say that we are going to solve all the governing equations like the Navier-Stokes equation and continuity equation by resolving all the eddies in this flow. So if you remember, when we talked about Kolmogorov theory, we introduced Kolmogorov's microscale, which is actually the scale that 99% of the dissipation of the flow roughly is kind of done before that. The flow is dissipated before that. So this is kind of the scale of the smallest eddies in turbulence, and in the atmosphere it's about 0.1 millimeter. So this means if we want to resolve all the turbulent eddies, our grid sizes have to be very, very small, up to about 0.1 millimeter or 2 times that. Okay. So what is the problem with this? The problem is we can show that the number of operations that you need to do at each time step to kind of resolve all these turbulent eddies using direct numerical simulations grows as the Reynolds number cube. And again, the Reynolds number, you know that is U times L over nu. But as you see, it's growing very, very drastically with Reynolds number. So in many of the applications, doing DNS is actually impossible given the current computational resources that we have. In fact, the highest Reynolds number that have been achieved using the existing computational resources and supercomputers in the world has been around 10 to the 4. And we have not been able, using these existing resources, to go further than that. And it's really impossible to do direct numerical simulations with current computational resources for some applications like studying these winds or atmospheric boundary layer, atmospheric flows that have very, very large Reynolds numbers. So in the atmosphere, you can calculate the Reynolds number. So assume a typical wind speed of 10 meters, and the length scale, you can say 100 meters or 1000 meters is the depth of the boundary layer, and then the nu of, you can put the nu of the air, and then you are going to get something around 10 to the 8th for the atmospheric boundary layer, which is the lowest layer of the atmosphere that extends from ground to about 1,000 meters above the ground, and where we have most of the turbulence. And after that, we don't have that much turbulence above the atmospheric boundary layer. So you see, with this 10 to the 8th Reynolds number, it's really impossible to do it right now, because say, look, it's not just these orders of magnitudes are going to be tripled because of this cube. So we need like 10 to the 24th, 8 times 3, 24th more computational power than, let's say, a flow with Reynolds number of 1. Okay, so this DNS is really impossible right now for doing these high Reynolds number flows. It's good for some low Reynolds number flows or Reynolds numbers below or 10 to the 5. So this is what we can actually do right now with the highest and strongest, most powerful computational resources in the world, super clusters. So what do we do instead? We want to solve this, right? So we want to find a way to kind of resolve the turbulence. So what we do is we introduce another technique which is called large eddy simulation. So large eddy simulation, what we do is we increase the grid size, or in other words, we decrease the resolution, our resolution. So in the large eddy simulation technique, we increase our grid sizes like to 5 meters or larger, or anything around that. And in that range, what we actually do, we resolve all these large eddies, like these purple eddies here. These are actually the energy containing eddies. These are those large eddies that have the largest energy. And then we model these smaller eddies that are like below the grid size, below the grid filter size, which are these red eddies. So this way we can save a lot of computational resources, and at the same time we can get some understanding of the turbulence behavior. So this is actually a novel technique, and it's been used a lot in these high Reynolds number flow studies. So we can actually resolve turbulence, but we also reduce the cost of computations, and therefore we can resolve turbulence for these high Reynolds number flows. Okay. So with this brief introduction, let's a little bit dive into more of the theory of the large eddy simulations. So what is it based on actually? It's actually based on the Kolmogorov theory that we talked about in the previous lecture. As we talked about in Kolmogorov theory, the large eddies are dependent on the geometry, while the smaller ones are kind of more universal. And we say one of the assumptions of Kolmogorov was that the small eddies we have a local isotropy in smaller eddies. And another assumption of Kolmogorov was that for high Reynolds number flows, we have separation of scales between the energy containing eddies and dissipation scale. So we have this kind of nice separation of scales if the Reynolds number is pretty large. Okay, so large eddy simulation employs this kind of property, and what it does is actually, because we have kind of universality here, and this dissipation range is not a function of the eddies, the shape of the eddies or the geometry of the eddies. What it does, it actually resolves only the energy containing scale. So we solve these energy containing scales, we solve the Navier-Stokes equation just for these large scales, large k numbers, low k numbers, and large length scales, and we actually model all these dissipation scales. So everything here is kind of modeled in large eddy simulations. And again, this is because we have this separation of scales, and then we have this local isotropy, because here everything is kind of universal. Like, it really doesn't matter which flow type you are, and the dissipation mechanism is kind of similar in most of the flow types, no matter what kind of flow you are studying. Okay, so this is kind of the premise of of this kind of large simulation technique and the theory behind it and why we are doing that. So now let me briefly talk about the three methods that we have for turbulence prediction. So we talked about DNS, direct numerical simulation. We talked about large simulation. We also have another technique which is known as Reynolds average Navier-Stokes equation, or RANS, which is at the other end of the spectrum for solving turbulence. So let's see what is the difference between them. So in the DNS, here we resolved and solved all the ranges of energy, from energy production, inertial range, and dissipation range. So we have very, very highly detailed information about turbulence, as you see here. In the LES, what we do is we resolve the large containing eddies here, up to here, as you see. We resolve those scales, and then we model the dissipation range, which is this part, right? So you have some information about turbulence, but it's not as accurate as DNS. At the end of this spectrum, we have RANS, Reynolds average Navier-Stokes equation, which is basically we model everything, all the scales, all the turbulence in the flow, from energy production, inertial range, and dissipation range, and everything is modeled. So we don't have that much information about turbulence compared to LES and DNS. Again, this is the energy spectrum that we learned and we talked about. So, and then here we have the inertial subrange, where we talked about the minus 5/3 Kolmogov's law. And so the LES cuts off here and then solves everything back in the before that wave number and then models everything after that, while RANS models everything and DNS resolves everything. Okay, so we have these three techniques that are widely used in computational fluid dynamics kind of community. So what are the major differences and main differences between these three methods? So in direct numerical simulation, we solve the full unsteady Navier-Stokes equation. As we talked about in the previous slide, we resolve the whole spectrum of scales, from very, very small scales, from about Kolmogov's microscale to all very, very large scales. And the advantage of this technique is that we don't need any modeling. We don't need any modeling. You just resolve and solve the Navier-Stokes equations. However, the disadvantage of this method is that the computational cost of this is kind of prohibitive for most applications, for example, for atmospheric band relators or high Reynolds number flows. So we cannot really do this for many applications. It can be just done for a limited applications where the Reynolds number is not that large. So the second approach, which is kind of in between Reynolds average Navier-Stokes or RANS and DNS, is large simulation that we talked. So in large simulations, the large eddies are resolved, but the eddies that are smaller than the grid filter size are modeled. The advantage of LES compared to DNS is that it's much less expensive than DNS, so we can actually resolve very, very high Reynolds numbers, like 10 to the 8th, the atmospheric band relayer. But the disadvantage of this compared to DNS is that we need subgrid scale modeling, because we need to model everything that is smaller than the grid filter size. Also, its accuracy is lower than direct numerical simulation. You see, you don't have all these scales. We don't resolve all these scales, all these small scales that were resolved in DNS. At the end of this spectrum, we have Reynolds average number Stokes equation simulations, which is called RANS. So in here, all the turbulence scales are modeled in RANS, so we don't have any resolving. It's least computationally expensive technique, so it's you can even run RANS with your computer. You don't need even to run it on cluster. It's so cheap computationally that you can even run it for most application on your computer. And in fact, it's the most widely used method in industrial applications. So most of the commercial software that you see, they use these RANs like ANSYS, Fluent, or a lot of this software, they use this RANS method because it's very, very computationally cheap, and also it gives the mean flow right. So it's actually what is mostly needed for many engineers. So that's why it's very commonly used in the industry. But the disadvantage of this method is that it has a large, we need to model a large number of closure terms in the RANS equation, the Reynolds average number Stokes equation. As we talked about, we have a lot of unknowns, and we need to determine them in those equations. So it's a lot of, you see, it's very, very flow dependent. So for each flow, you might have a lot of different closure terms and a lot of constants that you need to determine. And for each of them, these are all based on like some previous experiments that have been done. You need to determine those constants for different type of flows, like jet flows, boundary layer flows, or different types of flows. And this makes it a little bit complicated in this regard, because you need to know what type of flow you are simulating, what are the constants that you need to use for this type of flow. And the other disadvantage is that compared to these two methods, it has the lowest accuracy. So we have this spectrum where as we go from DNS to LES and RANS, the computational cost decreases dramatically, but also the accuracy of our simulations decrease as well. So here you see we don't have that much turbulence at turbulent eddies. We don't really model that much in RANS. It's mostly the mean flow that we get it right. So that's what is being mostly used in industry. Okay, so now with this introduction, I want to show some of our large eddy simulations that we actually do and have done in my group, so you get a better sense of different applications of these large eddy simulation techniques in different type of flows, especially environmental or geophysical flows that we are focusing on. So the first one is the large eddy simulation of complex urban atmospheric boundary layers. So here we have wind, and as you see, these contours show the velocity magnitude u in the streamwise direction. So it's just wind, and here this has been done by our in-house large eddy simulation code and by one of my colleagues. And as you can see, this shows that as the wind goes over these kind of complex urban environments, like we have trees or buildings, you see all these turbulent eddies, how they evolve in time, and these complex coherent turbulence structures and streamwise streaks that you can see here that are due to these surface roughness elements, and all these different turbulent eddies that are being actually resolved by this large eddy simulation technique. So it actually gives us a lot of insights into the dynamics of the winds or these complex environments, and it can be used for a lot of studies, for example, for ventilations or for in urban areas or urban design, or how how wind is actually evolving over these complex environments, or not just wind, but also you can look at temperature, scalars, and like heat equation or heat diffusion. A lot of these can be actually done using this large eddy simulation technique in over urban environments. So this second simulation is the one that I've done myself on using our large eddy simulation technique again. And this actually shows a hurricane landfall. So you see it's not just limited to urban environments. We can actually do a lot of different things. So this again shows the wind speed, and this shows a kind of cross-section of hurricanes as they landfall. So we have ocean here and we have land. So one thing you can see, this is hurricane motion. And one thing you can see is that as the hurricane landfalls, so we go from ocean, which is kind of a smoother surface, to land, which has a rougher surface. And the surface aerodynamic roughness length over land is much higher than over ocean. So you see that the wind speed decreases, and this is what we expect also. So here we have lighter colors, which show we have higher wind speed, but as the wind goes over land, the wind speed decreases, and we have darker regions here. So you see, we can study the hurricane turbulence actually here by this technique. So this is a very useful technique, and we can see how these large coherent turbulence structures evolve in time, and how they actually move and how they interact with each other, and also with structures and land and ocean. And we can study this turbulence to gain more insights into that, because these hurricanes are actually very important, because they can cause a lot of damage to coastal resiliency and coastal environments and coastal buildings as well. So you see how accurate and how detailed these large simulation can be, and they can help us to kind of study these phenomena. So it's not just air, we can also do water flows and look at large simulation of water flows. And this is actually, that has been done again in my group. And this is the large simulation of storm surges. So here we assume that we have storm surge. So in storm surges, what really happens is that because of low pressure of hurricanes, and also in the center of the hurricanes, it kind of sucks the water up over the ocean, and then because of these high winds, that water is kind of pushed toward the coast, and so we have these storm surges. These are very large surges that can be very, very dangerous over coastal areas. So we simulated this storm surge here, as you see. So we generate using large simulation code, it's OpenFOAM. And so here we generate waves, large waves at the inlet, and then these large waves kind of move and propagate toward the coast. And we did kind of a case study here where we'll also put a building. Actually, it's in Galveston Beach here. So we just took one building there and then calculated the geometry, the bathymetry here, and then we created these waves, and we wanted to see how these waves propagate and how dangerous they are actually for, like, especially for large waves. Like when the wave height goes beyond 6 meters, they become very, very dangerous. Okay, so you see these large eddies and these different turbulent eddies that are being resolved very well in large eddy simulation technique. And so that is one thing that we cannot get using RANS and commercial software. So here is kind of a zoom in. So we have zoomed in here. So you see that another part of the kind of the CFD codes is fluid structure interactions. So not only we have to kind of care about the fluid, but sometimes in some problems, like here we have storm surges that are kind of pushing the building. we need to think about also the fluid response and how it interacts with this flow, especially if these fluid force, the drag force of the fluid is very, very large. So here you can see in this technique we can even do fluid structure interactions, and we can evaluate the hydrodynamic stresses that are applied to this building. And as shown here, so this shows the stresses here, and you see stresses are larger, but they are also dependent on this turbulence. Sometimes you see these surges come, and then we have this kind of a big momentum bulge that suddenly kind of strikes the building, and so we have these large things, not only here but sometimes even higher, because we have this kind of some momentum bulges that can be completely chaotic and turbulent. So this is very important to also account for this turbulence in these kind of studies. And large simulation again shows that we can use that technique to kind of deal with this kind of problems. So these were just some examples that I have worked on in my group with our in-house large simulation course. But in fact, large simulation is very, very widely used, and you can look at it yourself. Not only here for designing a lot of like fluid structure interaction things like cars or airplanes or other things. Large simulations are being used a lot. For weather forecasting is also being used a lot, especially if you want to focus on some part. For wind turbines, wind energy, and a lot of other kind of applications. So this was one example here. So in the next session, I'm going to go through more details of these techniques, especially large simulations, and if we have time also on RANS, so we can study how they are actually being resolved and how they use different fluid equations, governing equations. Thank you very much, everyone.